Welcome to part 8 of this video series about this fantastic talking machine. So this is the synthesizer module, and I had to bring it back home to my lab for much deeper investigations and research because it just don't work. And as you can see here, I've added numbers to all the different PCBs, starting from number 1 and then all the way around, and back we go to number 26. So we got 26 different cards to play around with. So that is going to take a little while. However, if we start to investigate a little bit, some of them, for example this one, looks very much identical to this design. And oops, there's another one right there. So I figured once I know how those works, okay, I'm done with 4 of them. And I think it's also more or less the same with all those, except for the first one. That is different. And those with all the different inductors and stuff, that's probably either filters or oscillators. See here again, a lot of filter components. So this the filter design here actually goes again. Here it looks a little bit different. We got some more filters here. This one looks a little bit like that. Here we got again some filter components. And I mean, I'm of course going to look much deeper into all the fancy details here. This module also runs on 24 volts. 2 power supplies are actually individually driving the 2 positive 24 volts here. I guess it's for isolation, because this is an analog interfaced synthesizer. So to isolate stuff, they're using different power supplies. So the supply voltage goes up here. There's actually a little terminal here for power supplies. We also see the power supply wires going up here to a start point of supply voltage distribution, and then power supply also goes to the potentiometers. So this is actually manual input. So those switches, as you see here next to the pots, that is the way you enable manual override. Let me show you guys this here, it's easiest to see. This will be the analog inputs from the previous module. An analog input goes to this switch. So if I push this switch, that means whatever I want to control is now connected to my pot, to that one. And if I release the switch, the signal is now connected directly to the input. We got positive and negative going signals for each of the generator features, and that is, for some reason, you want to be able to manually override each of them individually by using 2 switches. I haven't yet figured out what is the purpose of that. Here we got like a global voltage setting using those resistors. I think this is the minimum and the maximum possible adjustment range you just set here, depending on the supply voltage, obviously. So that goes to those trimmers. So to figure out how this wonderful machine works, here's what I am trying to do. I'm looking at each module, and I'm trying to figure out what is in and what is out. And look at this. This module is only connected by 3 points, a ground, an output, and a positive. And as you can see, this is a sine wave oscillator. This is the classic bulb amplitude compensation. And those two trimmers, they do the frequency and the compensation circuit. And this is the output amplifier. And this generator makes a perfect 7.8 kilohertz sine wave constantly. So this output goes actually to two things. As you can see here, I think it's difficult to see. Let's get some light. So it goes up here to another module. And see, this module again is very, very simple. We've got ground and ground, so that was easy, right? And then there's only one other input, and the 7.8 kilohertz goes in here, and then there's an output. And the reason why I figure that out is this is also a modulator. So this is the second modulator. I call it the demodulator because they also call it demodulator in the published material, depending on which versions of the material you read. What we got here in the middle, that will be the 4 BAX42 diodes. They're coupled in like in a ring. They will be matched for all sorts of important parameters. This way this modulator works best. And we'll see two trimmers. Here I inlay the graphics from the report. That is a simplified version of the real thing, but it explains quite good how this is done. If you see on the carrier input, you see one transistor got a positive and a negative phase going to the diodes, and again that signal goes to the output. Again, two transistors amplify the signal, and here you got another trimmer for balance, and on the bottom you have the input, and again they're using two transistors to make a balanced signal to drive the mixer. So this is more or less how this mixer modulator is made. They didn't even use this ground or this positive. This is only for holding the wire and holding this series resistor. They figured out they needed a series resistor and a capacitor for local isolation and filtration for this module. See, down here is the positive input, and ground is all the way up there. So this is ground. So that wire is actually connected down here for the capacitor. So that's what they're doing. And so now we are a little bit later in the process. I've modified a little bit. I've connected ground correctly. I've added ground on the shielded cables on important signals. So there is a ground path or a return path to each of the important signals. Also, I've removed the capacitor and the resistor on the power supply, where they have added it right here, and then they used separate wires for grounding and stuff for that module. Of course, this is never going to work, and it's only going to make stuff much worse. So what I did is I put the capacitor and the resistor on the board, so the decoupling capacitor is local to the board you want to decouple. This is absolutely fundamental and very, very important to do that. Also, by adding series resistors to each board, that means now my power supply is not pulling AC currents. And when the power supply is not doing that, that means my ground is dead. So when I'm not pulling AC currents on the ground, then I can much more freely share the ground wires with other modules and this way interconnect in this kind of madness wire system that they're using back and forward with no returns and stuff like that. So the input to the output modulator is coming from this filter. So it's really easy. This filter only got an output, ground, and input. So let's take this filter to the bench and do some measurements. Took it over here, just like I did with the sine wave. And then this is now let's just look at it. This is a classic low pass filter. And this is very easy to see because the 3 coils, look at that, they're connected to ground. And then the input goes via capacitors, then capacitors and the inductor, and then capacitors again to the next inductor, and so on and so on. So obviously at 0 Hertz you get 0 output, right? So that means it's a high pass filter. So at what frequency is this working? Let's have a look. So this is 8 kilohertz. Let me just step 1 kilohertz to make this real fast. 7 kilohertz input, 8 kilohertz, 9, 10, 11, 12, and then it goes a little bit like that, right? So I think you can see the peak here, right? So I think this is a 12 kilohertz high pass filter. So this is obviously for some sort of a noise gating, probably. Why would you have a high pass filter of 12 kilohertz? It's getting more and more interesting. Let me put that back again. I'm still playing around with all the different boards and mapping what are they doing and how it works and all that. And I'm actually already soon going to explain you guys how it's all going to work, but let's just look at the first one here. This one is called voice. So this is the fundamental frequency or pulse generator, because this is a pulse generator, and it takes the voltage input from a potentiometer here. It goes via a switch where you can enable or disable the manual override. Else, of course, you take the banana inputs. So this is the voltage input, and this is the pulse output of this module. So let's just look a little bit on how it looks on the scope. So this is the control voltage, and this is the pulse output from that module. So let me see. So let me try and change the voltage, and then I only change the distance, the time between the pulses. So those pulses are used to kind of ring into the filters, and then the filters will generate the kind of the fill that you're hearing. So let me see if you can hear this. Can you hear the difference? And I got a volume for each of the features I'm adding. So this is just, let me crank down all this. Whew. So yeah, so far so good. This is the pulse that we see. It is really short. As you can see here, it's like 200 microseconds per division. So this is the pulse we get from the voice module, and it's only the frequency that it's changing, you know, when it's repeating, right? So let me zoom out. So here's the frequency, and if I dial this, whoa. You see, this is the time between the pulses. So let's just zoom in and look at the pulse. So again, the 200 microsecond pulse. So now let's look at the pulse from the pulse shaper. So this is a filter, and this pulse goes to this filter before it goes to the modulator. So now the pulse, this is the output of this pulse after the next filter, the pulse shaper. So obviously it is much wider, and now it's ringing. So, and this is just the same all the time. It doesn't really change no matter, you know, what frequency you adjust it for, right? So now let's look at the pulse after the modulator. So this is the about 8 kilohertz modulation, the carrier, and so the pulse goes to the modulator, and out comes the chopped up, as you can see here. Isn't that fascinating? Depending on how we look at it, it is now made into an 8 kilohertz. Let me see if I get like this, and then single. Then you'll see the pulse is now chopped. That is how it works. I think it is a little bit easier to show you guys the output from the modulator on a spectrum analyzer mode. Well, so now I'm in audio range from 50 Hertz to 20 kilohertz. This is the 8 kilohertz modulation oscillator input, and this is 16 kilohertz, the harmonic of the input oscillator. And obviously all this area down here, this is the output range after all the filters and stuff. So this is where the audio will be, right? So let me, right now I turned off the oscillator, the voice oscillator. So now the voice oscillator is on, and the higher, now I turn it all, up in the repeat frequency, and then you see what happens. So all those different frequencies, they kind of attack all the different filters, as you can see. So now it's a wide band input. See? So this is the maximum. And then I go down again. And this signal from the modulator here is what is distributed to all the different filters. In the process of adding really nice labels to all the different units, one thing that kind of bothers me is that most of the PCBs, they go in one direction, as you can see here, right? So that means the numbers, they will be up, and text will be this way, and it's nice and good looking. It's also important, you know, to be able to install the cards the right way, but some of them, they're actually mounted the other way around. Here's the oscillator module, and this is the wrong way. So it's just bothering me all the time when I pull and plug boards. They, as you can see here, so this is the oscillator. Oops, and that one must be installed the wrong way. So it's actually easy to do it wrong, because who is paying attention to how the socket is? So of course I'm just unscrewing the socket and mounting this the right way, like it should have been. There isn't really anything preventing me from doing that. All I have to do is just remove those 2 wires down here. So that will be the audio output that goes from the mixer module. Let's look a little bit more with a spectrum analyzer to see how the signals they look. So this is the output from the voice generator. So you see it's a broadband signal because it's modulated. And let's play a little bit with the frequency. This just changes the distance between the peaks. And this is, of course, the modulator at 8 kilohertz. So let's try and only play with one filter. So now I'm looking at the output from that filter. And here I got the level and the frequency of this filter. So there's both of them, that is like voltage inputs from the potmeters, voltage controlled, level and frequency. So let's do the same. So this is the output from that filter. I'm just gonna come with a little bit of signal. This is the modulator frequency, 8 kilohertz. So let's play with the filter. Can you see what happens? This is a higher frequency, more distance to 8. And when I go down closer and closer to 8, the frequency goes down, down, down. Because this is demodulated, it's actually the distance from 8 kilohertz that is generating the sound that we hear. You can also turn off. Let me see if I can. Yeah, let's try the noise input. And again, let's look at the input signal. So this is a wideband noise signal. And let's look at the output from the filter. I don't know if you can hear this in the background. I really tried not to make it annoying. But listen. This is exactly what happens. Whoa. And again, I got, of course, a level where I can crank down the noise, or I can crank down whatever is fed through the different filters. I am now playing a lot more with the different filters, and this is the filter for the noise that goes outside of all the other filters. So this one goes directly to the mixers and to the output. But there's also a frequency adjustment for that. And let's try and play. This is a spectrum of this noise output, and now I slowly dial on the frequency setting. So as you see, I get more and more of the lower frequencies, and this is all the way. So that is how it works. The frequency setting of the noise. Let me show you. So that is how it sounds. A lot of the problems I have with noise and instability is related to the pots. And there was actually one of the pot meters that was mounted in the front. That's this one. There was no wires connected to it, so that means, of course, I can take this out and let's have a look. It looks like it is completely sealed, and there's no way I can wash this. So how can it be this bad? It is just, they're just full of loose connections. So that is what I'm going to find out. I'm going to try and open this and see if I can see, you know, how bad is it really inside and what have we not. Let's get some more light. Okay, that could be a way to do it. So the rest is still mounted. Or is it really? No, it is. I don't get it. It's not looking like I'm supposed to pull this. Maybe it's like this. Yeah. Okay, that is gross. So that means it's supposed to... What? Let me try and clean this up. So this is probably... Oh... Yeah, there's definitely not a good contact anymore. So that is the... So look at that. It is that little part down here. This one, right? And up here we got some contacts. Let me see if, I think we should maybe take the top off as well. Then we can see what we got. Here it is, just turned into chewing gum. I mean, this is of course why there is no good contact. There's no way I can clean this because the unit is totally sealed. However, I could maybe open it just a little bit like this and just put in some cleaning and then assemble them again, but it's just cheaper just to replace them. So now I need to look at the cost to do that. And the time. This is going to take 1,000,000 hours to fix. As you can see, we got quite a lot of pots. Here is board number 7, the first Formant filter. As you can see, I've been drawing a little bit of lines so I could draw a full schematic of this unit, because I wanted to be able to figure out exactly what is going on, because there are a few modifications I wanted to do both for the frequency ranges and such, but See the changes I did? So I got a local capacitor on the supply and a series resistor of 10 ohms on the 24 volts input. Let me show you here. This is the original module without the modification, and you see the capacitor and the resistor is completely gone. And this is of course a big mistake, because a unit like this is very, very critical. There is no voltage supply rejection to the output, and so that means all noise on the supply rail will go straight to the output. I don't want that. I want nice clean sound. Let's look a little bit on the schematic from the published report for one of the Formant filters. So this is their schematic, and it is of course a simplified version that only shows the idea of how this is working. If you notice the two first trimmers on the left on the input, you of course set the level of the input impedance and the input level to your inductor. And that is a little bit interesting as well, why this is important. They got a very low impedance driver with an output impedance of only 4.7 ohms. And this drives the entire Formant filter section. And in series with each input here, there is a potentiometer on the front of the unit, and this goes to the in on this schematic. So of course the relationship between those trimmers here sets how aggressive is the input volume pot, and how much is then going on to the rest of this filter. So now you see a capacitor, a varicap. So this is a special diode where it's a capacitance versus a DC voltage over it is changing in a very well-defined way. And of course this is creating a resonant circuit. And then the signal goes to an emitter follower with a very high gain, and then a buffer. So the buffer transistor here is in the middle, and note the two outputs on that transistor. So there's a positive phase and a negative phase, and then it goes via two capacitors. One is only a DC blocking, that is the top one, but the bottom one, its value is very important and very interesting. And that value of that capacitor is exactly the same as the sum of all the varicaps on top. So of course you can see when you have 0 voltage on your diodes, you have the highest capacitance, and then it is the same as the bottom capacitor. So that means the positive and the negative phase zeroes out, and then you have 0 output. So this is how they created a DC variable level control. Here is the schematic that I've drawn directly from this PCB, so I know it to be accurate. This is exactly how it is implemented, and I also took the liberty to input with red numbers the DC voltages when the card is not mounted into the machine, so everything here is just open. I just want the DC voltages in kind of a non-connected state, so I could reveal all the positions of all trimmers, just in case I need to fix something in some of the other modules. It's important to have all the DC voltages and that thing's ready here. So here now it's much easier to see what is going on, because I put on all the real values of all components. But I think you get the point. Also, you see the 10 ohm resistor and the 100 microfarad capacitor I have added, And obviously you can see if this is not mounted on this PCB, any kind of AC noise on the 24 volt supply bus will obviously affect this circuit. It's going to go directly to the audio output, and so that was some of the reasons for the weird noise and hum and funny sounds, and that has been cured simply by adding those local filters to all the units. I want to show you some of the other modules that are like really cool designed. That'll be one of the 4 level units. I think you already got the idea, right? Yeah, you can see I added a series resistor and a capacitor local to the supply on this board because it didn't exist. And again, no voltage rejection existed on this board, and you cannot have power supply going directly into your audio. That is not a good idea. Well, let's look at the input. Goes to an emitter follower and see all the different resistor values and the diodes. See, the idea is the DC input, goes through an emitter follower and then drive the different diodes. And this way changes the attenuation. Isn't that just cute? I kind of like that idea. And then we got some DC blocking and a feedback capacitor from the output drive. Let me show you a schematic. This is a simplified schematic, again from the published report. It shows the design idea of this level board, and here you can see the point, all the different points that I set. And you can also see, I think I really like the way that they draw this schematic with the repeating diodes, just to make the schematic look more simple. Then you can just see the repeated diodes like that. So yeah, DC variable amplitude control, nice. So let's wrap this up a little bit and give you a fast tour around the 26 PCBs. The oscillator drives the 2 modulators. Okay. The voice module makes a tiny pulse. The tiny pulse is smoothened or made wider. Then it goes into the modulator. The modulator mixes this pulse with the 8 kHz oscillator signal, and this output goes to a level, DC controlled level. This is now mixed together with a noise generator. The noise generator goes to a level, variable level, and then this is mixed with the filters and the low level, a low impedance driver. So this is a 4.7 ohm output driver that drives all the filters for all the different frequencies and different levels of overtones you want to have. So those outputs, they are mixed. Some goes directly to a 6 input mixer. Some goes via additional voltage controlled filters. Okay, that will be the 2 first ones. So they are a little bit extra filtered. We also got a filter for the secondary modulator, and that output of course goes to the last mixer stage, and that's also our output. So we got two inputs for this mixer, and the other input is connected to another level unit and another noise unit that is controlled separately. So that noise do not go through the Formant filters. Let's look at the front and let's make a little sound demo. So for this very short sound demo, I have a tiny little amplifier and a little shitty loudspeaker. I cranked up the volume here entirely just to show you I need a little bit of more work with the different volume settings, as you see here. I don't know if you can hear this, but when I turn down the volume, I actually get a little bit on some of them. And that is because the output levels needs to be adjusted correctly to match the different capacitor values. So let me just see. Now we crank down the volume here because it's going to be real loud. So that would be the wideband noise generator. This one feeds the Formant filters. So let's listen to the Formant filters with noise. See, this is really difficult to hear that one. That one was the annoying one. So yeah, I guess you can hear, depending on the level and the frequencies, what's going on with noise. Okay, let's just crank down the noise. Let's play a little bit. Yeah, that is loud. So let me turn this down a little bit. Okay, now be careful. Yeah, okay, I think this is more than enough. So this is the drive level of the main carrier frequency. You can hear. Changes the feeling of the fundamental. I don't know. The idea is you're going to generate all the different sounds you can say using all those settings. I think it's a little bit hard to imagine just by playing with the different settings here, but at least that is the idea. I think in the next video we're going to try and see if we can assemble everything and see if we can make it talk.